Hello. So now we're going to code our entire neural network from scratch, starting way back when we talked about the sigmoid. But before we code in the sigmoid, we're actually going to import a library called Numpy. And this library is just going to allow us to do a lot of matrix math and a couple other things in a very succinct manner. It also has a very good random numbers package that we will be using. So now we actually can define our sigmoid. So we're going to do that now. We're going to define a sigmoid, and if you remember from the activity, we pass in x and a boolean as to whether it is a derivative of the sigmoid or not. And then we can set a value. We'll call it s is equal to 1 divided by 1 plus. This is our first numpy function, numpy.exp negative x. And so that's just going to be e to the negative x. Now we can set if derivative is equal to true. We'll return s, and then this is just the function for derivative. It's going to be this times 1 minus this. So that's for the derivative, and then return s if that's not true, because if this returns, it's never going to get here. This would be the same as saying like else. We don't need an else because this is already going to return that, so we'll just do it like this. So that's our sigmoid. And so now we're going to code in some input and some output data. We will call them x and y. Usually you just for notation's sake, you do capital X. And we're going to use numpy arrays to pass in our data, because it allows us to get matrices with columns and rows. So that's how you make a new row. Numpy. And you can sort of throw in any data you want. You just won't get the same results as me. I would keep it in this form, though, of 3 rows, 4 rows, 3 columns. I would keep it in that form. And then we're going to do y, which is going to be our output array. And this is going to be actually a transformed numpy array. 0, 0, 1, 1. We do this so that each one of these y values has a corresponding row of x values that lead to it. So that's all for our input and output data. Oh, that's my bad. Both of these need to be double bracketed. Yep. So everyone makes mistakes. I made one right there. When you make numpy arrays like that one, they all have to be double bracketed. So that makes sense. And actually, if we print x and y, you'll see it's in this form of columns and rows. That's the way the data is formatted. So you can check that, or you can do, I believe, x.shape will give you the same result. Yeah. Anyways, we're now going to move on to our weights and vectors. So we're going to set up a vector of weights as a vector of random numbers. And we're going to set the numpy to a random seed. And the reason we do this is to make sure our random number generator is not getting repeated values. And then we're going to use this line of code to set a layer of 3 weights with a mean of 0. So we do, I'm going to call this the synapse, because that's sort of what it is. We're not going to call it that. We're going to call it weights. I think that makes more sense as a name. What this is essentially doing is it's getting values from the NumPy random library. It's getting random values as a vector with dimensions 1, 3. So it's getting a 3-dimensional vector of weights, and then the mean of these weights is going to be 0. All right, so now we're going to create a big loop. And we talked about everything in our examples as if it was only happening once. But it's actually happening many, many times. And it's going to happen as many times as we have epochs. So we'll set our epochs over here. We'll set it to like 10,000 or something. Doesn't really matter for the first one. Remember that these things happen thousands of times in order to work. So the number inside the loop is going to be our epochs. That just means the amount of times you let a network run. In practice, you can set up monitors for our epochs, and that's going to automatically stop if our neural network begins to get worse. So next, we're going to set our first layer to our input data. This is layer 0, and it's going to be equal to x. So this is equivalent of passing in our data to our neural network. And then right down here, layer 1, so we're going to calculate our output layer. That's going to just be the dot product of the weights in our first layer. So that's just like we talked about in our weights and activations. And then we pass that into a sigmoid, remember, as this is sort of our activation function. Set this to false because we're not getting a derivative just yet. All right, so now we're going to calculate our error by subtracting our output data from the output layer. And then we can calculate our cost, which is going to be the error multiplied by our confidence. Sigmoid of our layer 1. And we set this to true because remember, confidence is going to be getting the derivative of the sigmoid. And then finally, we're going to update our weights based on, this is the latest thing we talked about. We're going to update our weights based on the dot product of the previous layer and the cost of their output, of the output layer. So we just add the dot product of layer 0 and our layer 1 cost. And that's all there is to it. We can then just print our output, which is layer 1, after this loop is complete. And that should be all there is to it. Yeah, you'll see that these values begin converging, and you can set these epochs to be higher, and eventually you'll be getting proper values. You'll see that we had 0, 0, 1, 1. These are converging on 9 and 2, 3, and 2. And if I move these up, they're going to converge even more on those values. Right. So that's all there is to it. I hope you learned quite a lot. You can just rinse and repeat that code and then print the outputs, and it's done. So just as a fair warning, this code might not produce values on the extremes of 0 and 1 unless you run it for a very long time, because this is a optimization problem. This problem will be fixed if you see like that. Well, it's e to the 5, so you can see it's going very down. So all these values are actually much smaller. These are both 0.9, and then this is like 0.000009. This is 0.00001, something like that. So these values are all very small. So this is an optimization problem. This is going to be fixed when you're using libraries like Keras built on TensorFlow, which I highly recommend when you're actually building neural networks. Conceptually, it's very imperative that you understand this code at the heart of neural networks. But when you're actually building them, libraries will take care of optimization issues like this. So as further resources, I've linked a video from Luis Serrano and a video from 3 Blue 1 Brown, and 2 articles that explain pretty much the exact same code in this video, as well as some slides which provide a very brief refresher on this entire series. I'm also going to include all the code for this video, and I'm going to include a folder which contains all of the documents that we used as resources and solutions to those resource documents. So thank you very much for watching. I hope you learned a little something about neural networks. And yeah, stay neural.